Okay, welcome to this wonderful, today's Wednesday, is it? Welcome to the wonderful Wednesday, July 28th, 2021. The fun continues. Okay. All right, so first, before we go into the single phase induction motor, we're going to have a little bit of review of what the impedance is, and I have a few slides that I got here. Now, my style is I sometimes read, so you can just read and follow. You can read and follow what I'm saying. So instead of me talking while you're trying to read. Okay. So anyways, okay. So impedance, we have three simple, very simple circuits here. We have the AC power supply in all cases, and to one of them we have connected a resistor, to the other one we have connected a capacitor, and of course the inductor or a coil. Okay, so it says consider a linear component such as resistor, so changes of the frequency of the source, so here's the source, do not affect the resistance of the resistor. The circuit is considered as linear, which means that the resistor will oppose the current flow in the same way no matter the frequency. Doesn't matter what frequency. The frequency changes, it doesn't affect the resistor. It's a pure resistance. The resistance is going to stay as it is. Okay, the resistor will oppose the current flow in the same way no matter the frequency. The current opposition equals to the resistance and with the designation of R. Nothing new to all of us. Okay, whoop-de-doo, there goes 2 minutes. Anyways, now consider a nonlinear component such as capacitor. So what's the difference between the linear and a nonlinear? So let's go here. To a pure DC source, a capacitor acts as an extremely high resistor. Okay, so put that in the back burner of your mind right now as we keep going with the single phase induction motor. Okay, so to a pure DC source, the capacitor acts as an extremely high resistor. What is another example of extremely high resistor when you have two terminals? All right. Well, the air. The space between that. It's also extremely high resistor. Between here and here, there is a resistor in the form of air. So that's the same thing. So to DC, the capacitor acts as an open circuit. Also nothing new so far. Right? The resistance is infinite. A broken wire, an open circuit. As the frequency of the source increases. So when we are going to apply, when this polarity of the source is going to start flipping back and forth with certain frequency, then the capacitor is going to start conducting. So as the frequency of the source increases, the capacitor's opposition to the current decreases. All right, so the current opposition, when we consider a capacitor in a circuit, it's called a capacitive reactance. So we're not talking about the resistance anymore. We're talking about reactance. Why is it called a reactance? It is because the resistance or the opposition changes depending on the frequency applied. So capacitive reactance with the designation of Xc is equal to 1 over 2 pi Fc, when F stands for the frequency, C stands for the capacity, and well, for now, we just have the capacity on that thing. Now, let's get another nonlinear component, such as inductor, which is this little guy right here. To a pure DC source, an inductor acts as an extremely low resistor. What is another example of an extremely low resistor? Well, a piece of wire. Okay. So when you apply DC to a wire, pure DC to a wire, it's going to be pretty much a short circuit. Yes, it's going to have some resistance because it's a physical component made out of a physical matter that exists on this planet. So yes, it is going to have some resistance, but in some cases, the resistance is so low that it's just negligible. All right, so okay, so to a pure DC source, as opposed to the capacitor, the inductor acts as an extremely low resistor. The resistance is nil, just as a straight wire or a short. As the frequency of the source increases, the inductor's opposition increases. So the more frequency at the source, the higher the frequency at the source, the coil or inductor is going to start opposing more. So it's reacting to what the frequency is. So we are dealing now with the inductive reactance. In both cases, capacitor and a coil, we are not talking about resistance anymore. We're talking about reactance. So with the capacitor, we're talking about the capacitive reactance. And with the inductor, we're talking about the inductive reactance. And of course, here's the formula that you all know by now, 2 pi FL, which, 2 is 2, pi is pi, F is frequency, and the L stands for inductance, and it is in Henrys, and the capacitance is in farads. All right, in all cases, what did I say here? In all cases of resistance, the reactance is, okay, so in all cases, resistance and reactance, the unit is ohm. So we measure that in ohms. We just express it in different ways. All right, so now resistor is a linear component because its resistive value remains unchanged if the frequency increases or decreases. All right, so we have that out of the way. Capacitor is a non-linear component because its resistance value changes if the frequency changes, and capacitor is not linear because resistance value changes. Well, that should be inductor here. All right. Inductor, all right, because of the resistance of the nonlinear components is affected by the frequency changes, we can say that the capacitor or our inductor has a reactive resistance. We call it a reactance. Inductors, inductive reactance XL, capacitors, capacitive reactance XC. Here are the formulas that we just talked about. All right, so now I multi-simmed a couple of circuits here. So I just connected a resistor in series because you need to have something to limit the current so things don't go out of control. So I just put a 1 kilo ohm resistor in series with the 1 microfarad capacitor. And over here, the waveform, I'm not sure you can see it or not, but the frequency of the power supply here, we have 100 hertz, duty cycle 50, so it's 50-50, amplitude 10 volts peak, and the offset is, I just made an offset of 10 volts. So the frequency is going to the power supply supplies the signal from 0 to 10 volts, right? Or actually 20 volts. There is no negative component in this here. And I put a Tektronix scope in the circuit. So I don't know if you know, guys, but you can actually measure current on the Multisim if you want, and you can hook it up with the scope. All you have to do is grab some component that's called a current probe. That's all. It's in the components list, and you hook that up, and you can see the current characteristics. So now I have zoomed in the next slide. So this is basically that screen right here with this capacitor. So so let's just quickly see what is happening. Of course, when you apply the power first, the capacitor is discharged, so it is going to act as a short circuit for a little bit. And because of the capacitor acting as a short circuit for the time being, then the voltage across the capacitor is going to be, here's the voltage across the capacitor, it is going to be pretty much nothing, because if it's a short circuit, what's the voltage across short circuit? 0, all right? Sorry, I apologize for using the word nothing. I always give you a hard time for saying the word nothing, and I just used it, okay? So all right, so the voltage value is 0 in the beginning because it's a short circuit, and then as the capacitor charges, the voltage is going to be equal to what the voltage is supplied. But so that's the supply voltage right here. So the voltage goes from 0 to whatever it is. Okay, so we're going to, in the beginning stages right here, we have 0 volts across the capacitor. And of course, because of that, we're going to have a maximum current flowing through it. Then as the voltage increases of the capacitor, the current decreases because the capacitor is charged. And then when it's after some time, I take 6 tau, you know that by now probably from other subjects, then the capacitor is charged, it reaches, the voltage reaches whatever the voltage supplied, and of course the current here is pretty much nil. It doesn't exist. All right. Then of course when the power supply goes to back to 0, then for the short period of time you're going to have another current spike, and the voltage is going to start decreasing because the current is going to start flowing. So in the capacitor, what we have is that the current leads in the capacitor and the voltage follows, right? So then you can say that the current and the voltage are out of phase with the current, okay? Voltage and current in the capacitor are out of phase if you apply, well, AC supply, or if you just apply DC from the time 0. Okay? And then if you keep applying the DC to a capacitor, it is going to stop conducting, and that's why it is considered to be a open circuit when we apply the DC. So, well, let's say capacitors love change. Okay, capacitors love. Let me just see if I can zoom this in here. Yeah, capacitors love change. The more often you change, the more the capacitor will work with you, right? And it will let you pass the current through it. If you stop changing and remain constant, the capacitor will stop passing the current. On this graph, I just explained what we saw. And if you want, you can go back and read it, but I just gave you the explanation of what was happening here, right? So in the capacitor, first you get the current, and then the voltage appears across the terminals. So instead of trying to remember the acronyms like Eli the Iceman or whatever, I don't even remember that acronym. I just understand what's happening in that part. So I think it's better than trying to remember some acronyms. Yeah, I just said now you can tell Eli the Iceman to go kick rocks because now you understand the concept. All right, funny slapstick. All right, there we go. So now we're going to take care of the coil or inductor. What do we have here? Same conditions with the power supply or the power source. Switch is closed. Once you close the switch, then this is going to happen, and this voltage, current, and the power supply is across the power supply is the power supply, and the voltage and current we're measuring across the inductor. So here is the magnified version of that. See that thing here? I just magnified it for the presentation purposes. So of course, as the opposite to the capacitor, as soon as over here, that's the starting point, like this moment right here, the voltage spikes of the source, the power supply goes from 0 to high, whatever that level is. Then the current is going to be pretty much 0 because coils hate change. They just want to stay the same. And if you change into something and the coil decides, oh, okay, we have changed the environment, we have changed things, but looks like things are going to stay for a while that way. So, okay, so I'm going to cooperate now. That's the way coil thinks. Actually, that's the way coil would think if it had a brain. All right. So when the supply voltage changes, all of a sudden, surprise, it changes. Okay. So then, of course, because there's no current, but there's voltage applied across the whole circuit. So of course, if we see no current, we're going to see a voltage spike. And then the coil is going to give in and start conducting. Right? And then because the current is going to start conducting, it's going to act more and more as a short circuit as opposed to the open circuit. So of course, when that happens, then the current is going to start flowing, right? Or the current is going to start flowing. And of course, when the more current flows through that, the less resistive that component is. So if it's less resistive, it is going to pass more current. So here are the graphs. Okay. Inductors, as a summary of this thing here. Here's the inductor L. All right. Inductors oppose change. The more you change, the more inductor will resist. All right. If you stop changing and remain constant, the inductor will eventually agree to the new situation, and then it will want to stay that way. Right, so every time you apply change, the coil is going to spite you. It's going to say, no, okay, change, no, okay, but stay that way, that kind of thing. That's the way coil would think if, as we said, if it had a brain. All right, so now there's the comparison of these two. Basically just what I said here. So what do we see here? Power supply changes. First, we have current. No, in the coil, first we got the voltage because we have no current. And in the capacitor, first we have current, and because we have high current, that means less voltage. They're just inversely proportional current and voltage. All right, so they are out of phase. Here's the key idea for today. When you apply a nonlinear component such as inductor or capacitor, then those things are going to behave in a nonlinear way, in a reactive way. And if you have a frequency present, then the current and the voltage are going to be out of phase. How far out of phase? Well, 90 degrees. Okay. 90 degrees, that's what it is. Now, just a little thing about the impedance. Since we mentioned one and the other thing, we might as well kind of wrap it up. Now, when there's those frequencies, at certain frequencies, we have certain frequencies and certain values of the capacitance and inductance of the coil. At a certain frequency, the reactance and the capacitive reactance and the inductive reactance are going to be equal to each other, and that's we call the moment of resonance. So the resonant frequency, for example, for this one here, capacitive reactance for the 100 microfarad capacitor and 100 millihenries, it is going to be somewhere around 50 hertz. That is going to be the resonance. What does it mean, the resonance? Well, they are having the same magnitude of reactance. However, because when we have the current, well, you know what, here, yeah, we'll get to that slide, and we'll come back to this. Right. So now, when we have both components in the circuit, and I scoped it on Multisim, the voltages across the capacitor and the coil, they are pretty much 180 degrees apart. Right? Because in the capacitor, the voltage is 90 degrees out of phase one way when we apply the change. And in the conductor, the voltage is going to be out of phase with the current 90 degrees the other way. So you go back to the whole extreme, and then the distance you have to travel would be 180 degrees. And it just confirms. If you want, you can do that. You can confirm it yourself on Multisim or using real parts. This just confirms that those two voltages across these two components are going to be 180 degrees apart. So at the resonant frequency, if those voltages are 180 degrees apart, what is going to be happening between this point And that point, between these 2 points, how much voltage are we going to have between those 2 points? Well, 0, right? Because they cancel each other. So at the resonant frequency, the reactances oppose each other, and they cancel each other at the resonant frequency, which means that whole thing is just going to pass things right through at certain frequency. Okay? Then if you go off the frequency, you're going to get more inductive reactance or more capacitive reactance, depending on which way you go. Okay, and so if you, and of course, if you go higher in the frequency, coils oppose the change, and the coils are going to give you more reactance. So it's more, they're going to be more resistive depending on the frequency. And if you go lower with the frequency, then of course the capacitor is going to give you more opposition to the current flow. But if you have in the middle, when the reactances are equal to each other, then the whole thing is going to be canceling each other. And those things, if you think about filters, that comes to mind, right? So let's see some of the graphs here. Here's the capacitive load. Here's the inductive load. So the R, let's see the resistance, pure resistance. We talked about the power factor. So that's a very similar way of thinking right here that we're going to apply. The resistance, let's say it's in both cases, the pure resistance that's at the angle of 0, okay, and the X and Y axis. Now, what happens is that when we look at the inductive load, remember when we had the voltage on the inductive load, voltage was the highest in the beginning, right? At the moment of change, the voltage was highest. And what do we need to have in order to have voltage? Well, we need to have some resistance. Because if you have no resistance across whatever it conducts or whatever you're dealing with, then you can't have voltage, right? So basically, well, the inductive reactance is going to be a 90 degree that way completely, okay? So when because the voltage goes higher, so that means the reactance goes higher this way, okay? And then, that is going to cause the reactance is going, whatever the reactance is, or whatever the resistance of the component is, and that's going to give you the magnitude of the impedance, all right? Now, when you have the other way, things the other way, the capacitive load, then of course the resistance remains of whatever the resistance, and mind you, that resistance, the pure resistance of that component is going to be very small, negligible, because, but if I wanted to draw it completely with proportions, it would just, it will be hard to present. Okay, so just remember the pure resistance is small in both cases. The graph would look much different. Okay, but so now when you go apply the frequency to it, the inductive reactance, when you're dealing with frequency, goes the other way, because first we have the current and then we have the voltage later. So that's why the reactance comes later. See, the reactance comes first with coil, and with the capacitor, the reactance comes later, based on the first few slides. So what do we say here? And of course, here is the magnitude of the impedance. So that would be the impedance. This would be pure resistance. This would be pure reactance. And over here, this is the impedance, and it does have an angle. Okay. So what did I write here? All loads are resistive, capacitive, and inductive based on this statement, the behavior of the load. Based on this statement, the behavior on the load, can't read what I wrote. Based on this statement, the behavior of the load in the circuit depends on the type of signal, which will be power applied, and the proportions of the load characteristics. Many components are considered to be dominant in certain way. For example, although a resistor has certain capacitive and inductive properties, its resistance is dominant enough that the other two properties can be considered as non-existent in most cases. Right? Then the same principle applies for capacitance in the capacitor. It's the dominant quantity in the capacitor, and inductance in the inductor. Right? So here's the impedance formula. The impedance of this whole load would be the square root of the square root of the resistance squared plus whatever the final verdict would be presented by the inductive or capacitive properties of the circuit. Now that's the Pythagorean theorem. If you look at this triangle here, then you can also apply the cosine of theta, sine or cosine of theta, depending on which way you're looking at it. All right. And that's the last slide as far as the impedance is concerned. Now let's switch to the next slide. The next presentation here, which would be the Control L for full screen as far as it lets me go. All right, so introducing the single phase induction motor part 1. All right, so first we're going to talk about the introduction. Hi, my name is single phase induction motor. It's not Friday yet. Okay, construction and principle, winding measurement, and we're talking about summary. We always have to talk about summary. All right, anyways. What are those? These are the power tools. What else? We're missing a grinder here. That's also a popular tool. So single phase induction motors are mostly applied in the power tools. Yeah. Where do we get the power? We get the power from the wall outlet. And of course, in a wall outlet, we do have a single phase AC, all right? And in order to make some motor run on the single phase, we have to have something that behaves like single phase induction motor, because we don't have the 3 phases in the wall that we usually have. So small power tools are being plugged in. You're not going to look for the 3 phase if you only have 1 phase. So whatever I said right now, okay? It probably makes sense somewhere. Okay, anyways, how many phases? Single phase motor. It is a single phase motor. Construction and the principle. All right, single phase induction motors. Very similar to the 3 phase motors, but they're different. They're almost like that, but they're different. The induction, okay, so somebody just popped in the induction motor will, with the wound rotor, and a single phase is almost like a DC motor, but with the AC. Yeah, almost. But we just provide the change of those windings, the change, the way the power is applied to the windings. It's solved a little bit different because we only have the DC, so we have to do something else, which means we're going to have a commutator, which is going to switch the commutator is going to switch the direction of the polarity of the coils by the way the commutator works. And we only have that the single we have DC. Now over here we do not need to use the we don't have to use the commutator because we do not need to change the polarity. The polarity changes itself because the power supply changes the polarity. So yes, it is very similar, but it's the same but different. But you know what, Rodrigo, thank you for pointing this out. That means you pay attention, and that means you're analyzing things as we go along. You will go far, all right, with this. Yeah, you and I, we can go places, right? With your smarts and my looks, we can do things. Never mind. Not Friday yet. Slapstick jokes. Okay, cool. All right. Yeah, so thank you. Thank you for that. I'm glad. If we don't have variable frequency drive in the lab, I would use the 3 DC generators to control. Okay. This is about what we saw. Okay, so if we don't have a variable frequency drive in the lab, I would use 3 DC generators to control the input frequency and the voltage of the 3-phase induction motor. Answering the last class question. Thank you. So that means you're paying attention. Yeah, but if you go 3 DC generators, no, that's probably, no, you know what? That would not work, because once you have DC, you have DC, okay? And you can't put a DC out of phase with another DC. So, so no. but I'm glad you're thinking, unless the crank is equal. Yeah. Oh, I see what we're thinking. Yeah, okay, 3 DC generators, because the DC generator introduces the pulsing, pulsing DC. So you would just, yeah, that would involve a lot of coordination, and it's probably doable theoretically, but there's another way. We're just using, how can we do that? All right, so I'm going to give you a hint. If you want to simulate a variable frequency drive in our lab with what we have, the machines that we have, I would use one DC motor, one DC machine as a motor in the beginning. That would be the first part of the equation. One DC motor. What else would you connect to what else in order to create a variable frequency on the output that would be applied to another machine? All right. Cool. Good. I'm glad you're following this. All right. So the construction of the single phase induction motor would be, well, it's got a rotor and a squirrel cage formation. Stator, single phase winding instead of 3-phase winding, because it's a single phase machine, so it kind of would make sense, right? And so we have on the stator, we have single phase winding, and we have something that is the new guy on the block here as the auxiliary winding. That sounds really intimidating. Auxiliary winding, you know, while you talk about that, you talk using those words, it's going to make you look smart, right? So run that, auxiliary winding. Okay, so what's the auxiliary winding? You can see this diagram here. So we have 2 types of windings here, the main winding and the auxiliary winding. So let's say the green ones, the green arrows, represent the Alan, I just want to move it. Here. Good. So let's say the green windings right here. Here's a winding. Here's a winding. Here's a winding. And of course, here's a winding. So look at the green windings. Let's say this would be the main windings for that. And look, there are, how many poles do we have here on the main winding? Okay. We have one sort of electromagnet completed and the other electromagnet. So if one is north, the other is going to be south. So we have 1 and 2 poles, 3 and 4. Right? So we got 4 poles here. The power tools or squirrel cage or wound rotor, that depends. Okay, sometimes you can get a squirrel cage, sometimes you get a wound, but it's just some of them are bigger, some of them are smaller, but the squirrel cage would be the most popular way for the rotor. Okay. Yeah, for the rotor. And just think about it. With the DC motor, you have brushes, so you have mechanical parts because the brushes are brushing against the commutator connections. So you have the mechanical parts rubbing against each other. So that means at some point something is going to break, something is going to get used. When it comes to induction motor, there are no, if you just use it as a motor, you can use squirrel cage. So there are no mechanical things supplying the power to it. Everything is happening by the magnetic field. Okay? So all you have to deal with mechanical is the bearings and mountings and all that stuff. So it's, I would say the life would be longer, maintenance-free life would be longer for the induction motor, for that reason. All right, so we have, just take a look at this. We have the main windings with the green arrows, and halfway in between, we have, they're interweaved with the auxiliary windings. So if you go from one way to the other, you have a main winding, auxiliary winding, main winding, auxiliary winding, main winding, auxiliary winding, and so on. It's just, they just interweave. Okay, so remember that. There's another thing here that we're going to look at. Something that's called a centrifugal switch. And the centrifugal switch is only used to start the motor. Look at the construction, the way it is made. We have some, come on. I just have to, when I move it, I have to touch somewhere outside of the picture. Okay, so we have a couple of connectors here, and what's this? Let's just think of this. This rotates around the center, and there are some weighted contacts touching something. So whatever they're touching, they're closing the contacts. Like for example, right? So once you start making, and these are kind of mounted in a pivotal way, so they could just open or close because they have a mass. As soon as this whole element starts spinning, then there is going to be eccentric force applied to that. And of course, those are going to become heavier and heavier that way towards outside of this disk. And they're going to become heavy enough that they're going to open. So how does this one work, this centrifugal switch? If this centrifugal switch is not spinning, then the contacts are closed. But once it starts spinning and reaches certain speed, then the contacts become open. All right. Also put in the back of your mind here. All right. So coils. What do we have for coils? Single phase winding main plus auxiliary winding start. They're just auxiliary windings are only used for start. What do we have here? Okay, we have the main windings, and you can see two coils, main windings 1 and main windings 2, which would be, they're split in half here, right? So you can well, actually, no, they're not split in half. They're just you can get both of them to get better power out of it. But they are just like those 3-phase transformers that we're using. You could use all the connectors, and there will be 2 wires in parallel wound. So that's the same thing as those 3-phase transformers that we're using in the lab. You were using before I came on board with this class. All right, so that's the main windings, and then there is the auxiliary winding. Okay, now the main winding here, they are pretty much both the same. Here are the main windings, and on one of the main windings there is something that's called a thermal switch. Thermal switch is normally closed. If you make the motor work too hard, in order to protect the coils from being burnt out, a thermal switch is being installed to basically open. So if the motor heats too much, it's just going to stop working on you, and it's going to not work for some time until things cool down and the thermal switch closes again. Right. So that's the idea here. Now, then what we have, that's the rod. Then that's the stator here. That's the main windings. Then we have a rotor. Around the rotor, we have also, so the rotor is a squirrel cage. So this is these are not windings around the rotor. These are the stator windings. Okay. Then we have the auxiliary winding. Look at what's happening. The auxiliary winding has a capacitor in series with it. And that CS thing, that's the centrifugal switch. What does that tell us? This automatically tells us once the motor picks up, if the motor is at the starting point, this centrifugal switch is connected. It's short, it's normally closed. So this coil is going to be working. Once, excuse me, once the motor starts spinning, then the centrifugal switch is going to open and this auxiliary winding is going to open. It'll be disconnected, and the only thing that is going to be in the circuit will be the main windings. Right. Here's the idea. Okay, now the idea of the single-phase induction motor is that because of the coils are arranged, where's that slide? Here. Because they are arranged this way, so forget, let's say, just consider choose main winding. Let's say the green ones are the main winding, and these do not exist. The auxiliary doesn't exist. The single phase AC is going to be applied equally. It's going to be applied equally at the same time to this two poles and this two poles. That is not going to produce a motion. The squirrel cage is going to get confused. There's going to be a bunch of things happening. Things are going to start canceling out. It is not going to start turning. Okay. Now, because we have a capacitor, in series with the auxiliary windings, what's happening? When we talked about the impedance, we're going to shift the voltage or the current, let's say, 90 degrees out of phase. Well, now we're doing something. Now we got something to work with, because these here are going to be always 90 degrees out of phase from each other. So here's the main, and here is current supplied to the main, and then 90 degrees out of phase, we're going to have a current to the auxiliary, and then the main and auxiliary, and the main auxiliary. So then we can, that way, we're going to put things into motion, because we have the 90 degrees phase shift between the currents supplied to the windings, which are interweaved. And we only need to apply the power for the auxiliary windings at the start, just to make it start. Then once things are in motion, then the single phase can just work as it is, but because the motion is already happening, it is going to settle down, and those main windings are going to hit the single phase at the right time, and the motion is just going to be they're just going to be supported by that. If you stop the motor, then the centrifugal switch is going to close, make a contact again, and then you're ready to start that again. If you have a grinder that at home, like garage or somewhere, you press the switch, you're not, you press the on button to turn it on, you're not going to hear much of a clicking happening. But listen to what happens when you close, when you turn the machine off, the grinder, just a regular grinder that you just, you can sharpen your knife on it, or adjust the shape of your screwdriver. Listen to what happens when you turn it off. The speed, of course, is going to decrease, 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 and it's going to go slower, slower. And then at some point, you're going to hear that click. That's the centrifugal switch closing back again. You're not going to hear it opening because there's going to be too much noise, and the opening is just releasing things outwards. So, and there's all other noises happening, so you will not hear it. But when you turn it off, it's going to go click. All right. So that's the centrifugal switch. So I hope that I'm explaining this thing right to you. If not, go back and listen again. Now, when it comes to, so that's why we have the capacitor going on here. And here's that centrifugal switch in the main, the auxiliary winding. And here's the main windings. You can use just one, or you can use two of those. If you use two, you're just going to get more power. That's how the machines are designed. You're just going to get a machine that's a little bit more powerful because they're one on top of each other. Right? And if you just you so alphabet, you're just not going to use as much power. All right. So if you use just one, try to use the one. You're supposed to use the one with the thermal switch. If the machine, because if you just use the one and you connect the second, the second main winding that is not connected to the thermal switch, you are putting yourself in a dangerous situation that you can burn out the coils if the motor overheats. Of course, that switch is going to open, but that thing is not connected. It's just this thing is connected, right? So if you use a single one, use the one with the thermal switch. Right, so let's see what numbers we have associated with this whole thing. Stator, single phase main, single phase winding, the main plus auxiliary winding just for the start. And once the motor starts, the centrifugal switch is opening and the auxiliary windings are disengaged, and the motion of the rotor creates the timing difference at which those coils are going to hit the magnetic field is going to hit the squirrel cage, and the motion will be sustained. Right? Then you can turn it off, and if you have still some motion, you can still turn it back on, and it's going to resume the motion. But if it slows down too much, pretty much when it comes to almost a stop, then you will need to engage again the auxiliary windings. So do we have so we have the winding, capacitor, and the centrifugal switch. Synchronous speed of the at the stator, well, that doesn't change. It's the synchronous speed would be 120 times the frequency over the number of poles. And of course, because it's an induction motor, remember, we are going to talk about the slip. Okay, and what's the slip? Slip tells us how much slower the rotor spins in comparison to the revolving magnetic field, which would be revolving at the so-called synchronous speed. So we're calculating this thing the same way. It always will have a slip. Induction motors always has a slip. Synchronous motor will not have a slip because it's the strong magnet synchronizes with the revolving magnetic field. That's why it's called synchronous motor. The induction motor depends on the changing magnetic field caressing the metal rods, inducing EMF, which is going to induce the motion in it. Okay, so we're always going to have a slip. Now, here's the starting thing. This slide is basically what I just explained to you about 5 minutes ago. Torque versus speed, here's a curve. Torque versus speed, curve, all right? Same as the induction motor that we talked about. Operating, the speed, the rotational speed would be about 95 to 97% of the synchronous speed. So that's pretty good, I would say. Then the starting torque would be 0, and this is what we're talking about, because the windings, the two poles, are just like a cross configuration here, and they're being hit at the same time with the single phase. So there is no anything revolving there. So we're not going to have a starting motion. That's why we need the auxiliary windings to start it, and then we disengage those. So starting torque is going to be 0. What does that mean? The motor cannot start by itself, needs some special arrangements to start, and this is auxiliary winding that we just talked about. Okay, so this one went fast. All right, winding measurement. Sometimes, if you just have a motor, how would you find out just using an ohm meter which would be the main windings and which would be the auxiliary windings? Well, if you just have an ohm meter, what do we have at the if you have a multimeter, you switch it as an ohm meter, you have a little tiny bit of a DC supplied on those probes. So can you find which ones are main and which one is the auxiliary winding? So remember, we have two main windings and we have one auxiliary. Well, the auxiliary winding is going to be one that's open, right? Because you have a capacitor there. And when you quickly reverse those, you're going to have a little bit of a spike, but digital multimeters is not a way. Sometimes you need an analog meter to actually, if you really want to see the reverse spike on that, when you quickly reverse those. So that's how you can find, because it has a capacitor. So to a multimeter, ohm meter, this is going to act as an open circuit. And these two are going to act as pretty much a short circuit, because it's a lot of wire, but still it's just wire. So you're going to have some resistance, but it's going to be a low resistance, all right? So main windings will be shorted, auxiliary windings will be open, okay? So here's the point form of that. Windings impedance, and we talked about the impedance, all right? So Z is the designation for impedance, and it's a combination of resistance and reactance, and it's going to have the magnitude of the resistance that is pretty much the derivative of the resistance at angle 0 plus the reactance. So that's the complex. That's the expression in a complex number. You can also express that in a complex number. We apply AC voltage, so Z is the Z. The impedance is going to equal to whatever we have measured as AC across the component, and then whatever we measure as the AC current going through that component, and that's going to give us the magnitude of the opposition, which would be the impedance, which would be the combination of resistance and reactance. Now, when we apply the DC values, we're going to get the resistance of it. So if we apply the DC values, we're going to have the voltage, that is DC voltage, and the DC current. From that, we can have we can substitute the numbers for the resistance. We can substitute the numbers of the impedance of that, and the total impedance is going to be that is going to give us the reactance of the particular component in the circuit. How to lower the voltage in the lab? Well, we're not performing the lab. Okay, now we are going to apply the AC and DC to both circuits. And that's it. Would we apply DC voltage to the auxiliary winding? Yes or no? Of course, we're not going to apply the DC voltage, because I just wrote what I told you. To the DC voltage, the capacitor is going to make it open. All right. Now here's the. It says Rodrigo says, but with the three-phase, it is self-starting. Yes, the three-phase induction motor is self-starting, because the three phases are arranged in 120 degrees out of phase with each other, which when we apply three phases, we're going to create the revolving magnetic field. So that's the thing. In a three-phase, we have the luxury of having the revolving magnetic field right away. In the single phase, we're not going to create the revolving magnetic field right away because we won't be able to make it spin around the stator because we only have one phase. So it's just like a pulsating field, but that stands still. Okay. So that's why we need to introduce the out of phase auxiliary windings just to start it. And once you start it, we just disengage that, and the motion is going to make it. So the rotor is going to hit the magnetic field, pulsating magnetic field at certain times, and it's going to sustain the motion. Okay, so that's why. There are different ones as far as the electric cars. In some cases, the synchronous motor is applied. In some cases, there will be induction motor, but with the wound rotor applied. And in some electric cars, also there would be the DC motors. Yeah, or brushless could do that because by varying the frequency, you can yeah. So there are different approaches to that. Okay. All right, so a little bit of example. We're almost done. You know what? Just analyze that example, because that's the last slide. I know you have another class to go. Analyze this example. This is in your post-it notes. Pretty straightforward. The key idea to that is, in order to measure the resistance, the DC component of the whole circuit, you apply the DC, and then you are applying the DC values that you measured, and that is when you're dealing with the DC and pure resistance. Now, when you want to measure the reactance, find out the reactance, you're applying AC component into that, and then you're measuring the AC voltage and AC current. You will get different values with the same components because we have the coils and we have the capacitor involved in that. So you will get different values when you apply DC and AC to the same circuit, and based on that, you can get those magnitudes of this of the quantities, and you can substitute them, and then you can just get the complete reactance of the particular equipment. The piece of equipment here or component would be the coil here. But in order to do that, if you just connect the complete AC to this or DC to this coil has very low resistance, you might burn out the coil. So we're introducing a resistor in series just to slow the current down. Okay. All right. So that is the summary, and with the summary, you can just read what I said, and that's pretty much the end of today's lesson. Look at that. We are 1 hour bang on time. Okay, you guys have another class to go to. Thank you very much, and I will see whoever, whatever the first group for the last lab, which will be the induction, induction motor today. Okay, thank you, and I'll see you when I see you. Bye, guys.